Hello guys and welcome to my channel. This is going to be the first video tutorial that I'll be posting for my channel, and what I intend to do for this video tutorial is to cover the first unit of the IGCSE Computer Science Curriculum following the Cambridge IGCSE Computer Science textbook. Just a brief overview guys, my name is Miss Alicia and I'm an international teacher teaching for 6 years and a half now in different countries. Focusing on different subjects from the IB biology to the IGCSE computer science and IB computer science, as well as math and the IGCSE chemistry. So I've gotten through different situations where I've found that students are trying to seek different ways to support them on topics, especially for this subject domain like computer science, and they don't exactly find that on different online sources. So I decided to create video tutorials that sequentially explain these topics and use different type of visual aids and verbal explanation and also practical application in terms of Python programming and Java programming, which I intend to, to upload more videos for. Without further ado, guys, I'm going to be opening the computer science textbook. So this textbook is the typical standard textbook for computer science. If your school offers computer science, you're pretty much going to see that this textbook is available at your school library or something available with you even right now. If you can't find this textbook, guys, then you can definitely find the e-copy version online. Just a quick note, I would be covering the topics that are mentioned here sequentially, starting from binary systems and hexadecimals up to security and ethics, and also up to databases, because that's on chapter 13. So I'm pretty much going to cover all the topics on this textbook sequentially using verbal aids and explanations. Oh, there they are, guys. These are the topics. So from chapter 1 up to chapter 13 is what I intend to cover. I'm going to start by explaining chapter 1, and it focuses on binary systems and hexadecimals. And basically, it explains what binary systems are, and basically our, denary system that we currently have, which is the number system. So we're going to be looking at why do we have a binary system, how are conversion made from binary to denary, denary to binary, hexadecimal to binary, and binary to hexadecimal. We're going to be looking at the conversion steps that involve these changing from one form to the other. We are also going to be looking at why we actually use a binary system in the world of computer science and how is it applicable in real life situations. So first, we're going to be looking at the denary system, which is what we call the base 10 system, and it's made up of the multiples of 10, starting from 10 to the power of 0 up to 10 to the power of 4. So this is the typical system that we have, that we use all the time when we're counting things or adding things together. We use the denary system, or we also call it a decimal system. In this case here, we have denary system as a base 10, and it's basically made up of the multiples of 10. But when you oppose this to binary system, it is the opposite. Binary system is based on the number 2, and it consists of just 2 values, which is 0 and 1, and that's what we call bits in computer science. So why do we have 0 and 1 in the first place? How do we apply this practically? If you look at any digital device or any robotic device, they contain microprocessor chips, and these microprocessor chips receive instructions from us. But the instructions they receive from us is analog, they're not digital instructions. Those instructions have to be converted into zeros and ones, which is called bits. And basically, the computer would understand a 0 either as yes or no, yes for example, a 1, and a 0 as no, or switch on for 1 and switch off for no. So there are different instructions. Any single instruction that we need to input into the computer system, or we need a specific digital device to perform, has to be converted into binary, which is basically into bits of zeros and ones. So the binary system basically starts from 2 to the power of 0 up to 2 to the power of 7. So 2 to the power of 0 equivalents to 1, 2 to the power of 1 to 2, 2 to the power of 2 to 4, 2 to the power of 3 to 8, 2 to the power of 4 to 16, the power of 5 to 32, the power of 6 to 64, and the power of 7 to 128. So this is pretty much where the binary system ends. You notice that it stops at 7. We know that 8 bits, basically 8 ones and zeros, make up 1 byte in a computer system to store instruction. So if you've noticed right now, you notice that we started with 0, because this computer always starts the count from 0 up to the maximum end. So we started with 0 and we ended with 7. If you count it with our normal denary system, would go 1, 2, instead of starting with 0 from the right, we're going to go 1, 2, 3, 4, 5, 6, 7, 8. We get the 8. But because the computer starts always counting from 0, we get up to a 7. So if we had a typical binary number like this and we wanted to convert it into denary, how would that work? So that's the question. The first conversion we must understand is how do we convert a binary number into denary? So to understand that, we're going to be using this activity 1.1. We're going to be doing 2 examples together from here, and then I'll ask you to do from C to J on your own as a practice work if you've understood what the conversion rates or how the conversions have worked. I'll be using Jamboard to visually explain this because I feel like when I visually explain this, even for my students, they understand much better. So that's what I'm going to be doing right now. So I'm going to be writing the activity, and this is 1.1. And basically what we're doing is converting binary into denary. So I'm going to write it here, binary, and that goes into denary. Okay, so sorry about that, my Y, there. So our first example, guys, is example A, or should I say question A. So 1.1 question A. And we have a binary number, which is basically 0, 0, 1, 1, and then we have 0, 0, 1, 1. So if you have an exam question or a test question or anything that has to do with you to convert any binary number into denary, it pretty much follows a straightforward method, which I'm going to be talking about. First of all, you have your binary number. You have to recall that the powers of 2 go from 2 to the power of 0, which we've seen, up to 2 to the power of 7. So just make sure you recall that. Make sure you also remember what the powers of 2 are. So remember that they go from 1 up to 128. So just a recollection of what we've just seen now, because you're going to need that when you're converting. So this is something you should always put at the back of your mind when you're trying to convert binary into denary or denary into binary, which is what we're going to see a bit later on. So let's work on to our conversions. First of all, we're going to be using the first step to convert any binary number into denary is to write the powers of 2 going from right to left. So we're going to look at right to left in this direction, and we're going to be writing the powers of 2 on top of those bits. Remember that a bit is either a 1 or 0. So we start with 2 to the power of 0 from right to left, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, and, oops, there's my 5, 2 to the power of 6, and finally 2 to the power of 7. So we must write all the powers of 2, that's the first step, on top of each bit that we have, okay? So that's like very essential. So we had 2 to the power of 0, to the power of 1, to the power of 2, to the power of 3, 4, 5, 6, 7. So you notice we have a total of 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So 8 bits actually make 1 byte of memory storage. And that's pretty much how instructions are stored, depending on the amount of bits. They're not necessarily all stored in 8 bits. They could be stored at 12 bits. They could be stored 64 bits, depending. So, but just remember that 8 bits always make up 1 byte. So now what we're going to do, when we've written the powers of 2 on top of each bit, we're going to multiply that by the power of 2. So the first one, we can look from left to right in this case. So the first one is 0 times 2 to the power of 7. We know 2 to the power of 7 is 128, times 0 is going to give you a 0, so we're going to write 0 here. 0 times 2 to the power of 6, we know that 2 to the power of 6 is 64. Again, if you're not sure of where I'm getting these powers from, remember we saw them here when we were looking at the powers of 2 going from 2 to the power of 0 to 2 to the power of 7. So 2 to the power of 6, as we mentioned, is actually 64. When we multiply that by 0, we get a 0. 1 times 2 to the power of 5, right? Because remember that this is 2 to the power of 5 here, guys, in case if you can't see. It's 2 to the power of 5. So 1 times 2 to the power of 5 is actually 32, because 1 times 32 is 32, so we're going to write 32, and we're going to put a plus sign here. You can put a plus sign between the zeros, of course you have to, because why I didn't put a plus sign is eventually I don't even have to write the zeros because they still give you zeros, so they don't really add up to give you anything or add to the total. So if you want, you can just leave the zeros out. When you multiply, once you see anything that contains a 0 with a power of 2, you don't have to count it out, you just leave it out and you start with the ones that contain the 1. So 1 times 2 to the power of 5 is 32, and you put a plus sign. 1 times 2 to the power of 4, remember that 2 to the power of 4 is actually 16, so 1 times 16 is 16. and then plus again. We're moving from left to right, don't forget. 0 times 2 to the power of 3 is 8, so that's going to be 0. 0 times 2 to the power of 2 is 4, that's going to be a 0. So I'm not going to write them out because there is no sense in writing them when they still give you a 0. 1 times 2 raised to the power of 2 is going to be a 2, plus 1 times 2 raised to the power of 0, which is going to be a 1. So now we're going to add up all what we have. 32 plus 16 is a 48. Plus 2, it's a 50. Plus 1, it's a 51. So we finally get a result as 51, which means this is the correct answer when we try to convert this binary here into denary. So that's your answer. So the steps is, we're going to do a second example, but just to recall of the steps, always remember to put your binary powers from right to left on top of those bits as step 1. And then you multiply those bits by the power of 2 to get your final denary answer. So we're going to look at another example. So we're going to go to example B, or question B rather. So question B says we need to convert 0, 1, 1, 1, 1, 1, 1, 1 into denary. So we're going to do that here. So question B. So we have 0 and we have 7 ones. 1, 2, 3, 4, 5, 6, 7. And so that's exactly what we have here, 0, 1, 2, 3, 4, 5, 6, 7. We're going to convert this again into denary. So we repeat the same steps as we've done before. So pretty much what we've done is we've put the powers of 2 from right to left. So we're going to do that again. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5. Sorry guys if this is really close, but I'm trying to make sure they're on top. 2 to the power of 5, sorry. And 2 to the power of 6. And finally, 2 to the power of 7. So 7. I'm going to write this 6 well. There. So we have all powers of 2. So that's the first step. Write your powers of 2 from right to left. And then the next step is to multiply those bits by the powers. So we're going to multiply them starting from left to right this time. So the multiplication goes 0 times 2 to the power of 7, which is 128. Automatically, 0 times 128 is going to give you a 0, so we're not going to write it down. There's no need. If you do write it down, it's just going to add up to the same total. So 1 times 2 to the power of 6, which is 64, plus 1 times 2 to the power of 5, which is going to be 32, plus 1 times 2 raised to the power of 4, which is going to be 16, plus 1 times 2 raised to the power of 3, which is going to be 8, plus 1 times 2 raised to the power of 2, which is going to be 4. Okay, 2 to the power, I'm just checking guys, 2 1 to the, yeah, it's going to be 4, sorry. Plus 1 times 2 raised to the power of 2, which is 2 raised to the power of 1, sorry, which is going to be 2. And finally, plus 1 times 2 raised to the power of 0, which is going to be 1. So again, guys, I know it might not be really clear, so I'm just going to repeat it here again. So we had this number initially, 3, 4, 5, 6, 7. And what I said we needed to do was just to put the powers of 2 on top. So we started with 2 to the power of 0. So I'm just making it clear here in case you can't see the first one. 2 to the power of 1, 2 to the power of 2. So we put the powers from right to left. 2 to the power of 3, 2 to the power of 4, and 2 to the power of 5, and finally 2 to the power of 6 and 2 to the power of 7. So this was what we had on the first example, just to maintain clarity. So what I did was I multiplied these bits by the powers of 2, and I said the first one gives you a 0, so that's why I have this 0 over here, okay, for this one. And then I said the one here, 1 times 2 to the power of 6 gives you 64. And then I said 1 times 2 to the power of 5 gives you 32. 1 times 2 raised to the power of 4 gives you 16. 1 times 2 raised to the power of 3 gives you 8. 1 times 2 raised to the power of 2 gives you 4. 1 times 2 raised to the power of 1 gives you 2. And 1 times 2 raised to the power of 0 gives you 1. So that's pretty much how I got there. Now we're going to be adding up all our numbers. So because we now have our answers, when we multiply the bits by the powers of 2, we have to add them up all together. So the first one is 64 plus 32 is going to be a 96. A 96 plus 16 is going to be a 112. A 112 plus 8 is going to be a 120. A 120 plus 4 is going to be 124. 124 plus 2 is going to be 126 plus 1 is going to be 127. So your final answer, guys, is going to be 127 when you convert this binary number that you have here into denary. And that's how you do it. So again, a quick recap is the first thing you need to do is when you have your binary number, put the powers of 2 on top of each bit that you have from right to left, multiply those bits by those powers of 2, and finally add them up to get your denary value. So I hope you've understood these 2 examples that we just did right now from activity 1.1 on how to convert binary into denary. What I suggest you try to do, guys, on your own is to do from C to J, following these steps that we just did now to see if you can convert it. What I plan on doing in the upcoming video tutorials is that every week I'm going to be doing a sort of pro bono where I ask some of my subscribers to be able to send me I'll assign a task on the topic that we finished or activity that we've done just to recap and test and see if you actually understood it. And then at the end of the week, I'll only accept 5 people's, basically for now, I'll be accepting 5 people's work, like a feedback after you complete the activity, so that I can return to you a feedback if you would like that. So that's what I'm planning to do, kind of like a feedback, because that's going to be easier and that helps a lot of students, and I hope it helps you as well, that when you complete a task and you follow the steps through on something and you complete it, you actually want to see a feedback or you want to check if the answers are right. So I know there is a marking scheme for this textbook online, but still, I would give tasks that do not contain questions from this activity so you can practice to check and see if you actually understood what we've done and what we've been doing so far. So I hope to do that in the upcoming video tutorials. I'll let you know when that task is up for you to download in the description or to check out in the description and complete. Okay, guys, the next thing we're going to do for this video tutorial before I end it is this part on 1.2.2, which is how to convert denary into binary. So we're going to move on here. So we want to convert denary into binary. So I'm going to write it down. So we have denary and, oops, my D looks like an A. There it is. Convert it into binary. And the steps we're going to be doing is different from what we just seen in the previous slide here when we're converting binary into denary. So what are the steps? So the first thing, there are 2 methods. When you have a denary number, which is what we call a decimal number or a typical number system that we use, and you want to convert it into binary, either you divide that number by 2 and you keep your remainders and you look from bottom to top. I'll explain what that means. Or you could actually do a second method, which is pretty much what my students normally pick to do. You can use any one, but this one is pretty fast and more, kind of accurate. The second method is you look at the powers of 2 going from 2 to the power of 0 to 2 to the power of 7, and you see which powers of 2 can actually add up to give you that denary number. So we're going to look at the second method. The first method has been given to you here to explain. If you wanted to convert this denary number of 107 into binary, of course you're going to be dividing this, sorry about that, guys. You're going to be dividing that number by 2. So in this case, you're dividing 2 by 107. You get 53 remainder 1. So you're going to keep dividing by 2 until you no longer get a remainder. And then you're going to be looking at those binary numbers that you get finally from the remainders, looking at them from bottom to top and writing them out. So this is one way you could do this. Another way you could do this is what I'm going to show you now. So we're going to do activity 1.2 and we're going to take the first example. So activity 1.2, we're going to go by example A. If we wanted to convert this number 41, which is a denary number, into binary, what can we do? So what are the steps? The steps are, you must write out the powers of 2, starting from 2 to the power of 0, as we saw before, up to 2 to the power of 7. So 2 to the power of 0, 2 to the power of 1, I'm going to write them at the bottom here. 2 to the power of 2, 2 to the power of 3, 2 to the power of 4. Oops, my 2 there was really long. 2 to the power of 5, 2 to the power of 6, 2 to the power of 7. And that's pretty much what we're going to be writing for the powers of 2. So we're going to write the equivalent values for these powers. We know 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16, 2 to the power of 5 is 32, 2 to the power of 6 is 64, and 2 to the power of 7 is 128. So how do we convert this number into binary? So what we're going to do is we're going to be looking at which one of these equivalent values from the powers of 2, when we add it up, it actually gives us 41. So we start looking from left to right. So we're going to start with the first one, 128. 128 is bigger than 41, so you're going to make a comparison here. 128 is bigger than the number we're supposed to change into binary, which is 41. So we're going to put a 0. So essentially, 0 is going to mean a no, as in it's bigger or smaller, and then 1 is going to mean a yes. Remember I mentioned that the computer is a digital device, and as such, it only understands machine language, and that basically is represented using zeros and ones. So 128 is bigger than 41, which means it cannot be used to add up to give you 41, so we put a 0. We look at the next number from left to right. 64 is also bigger than 41, or is greater than 41, so we're going to put a 0. 32 is actually smaller than 41, so that's actually a yes. It actually can, add up to give you 41 because it is smaller. So when it's a yes, we put a 1 on top. And then what next you need to do is you need to subtract the number that you said a yes for from the number that you're trying to find the binary value of. So we're going to subtract 32 from 41. When you subtract them, you get 9 as your answer. So you're left with 9. You're still left with 9. Your remainder is not yet 0. Just like what I explained, what I showed you guys in the first example or first method of how to convert denary into binary, I said that you keep dividing by 2 until you no longer get a remainder. It's the same thing here for the second method. You keep looking for the number that you add up to give you that denary number until you no longer get a remainder, or when you subtract that number from it, you no longer get any value, but you get 0. So we said 32 is smaller than 41, and we subtracted 32 from 41, we got 9. So we still have to keep going and checking which power of 2 can add up to give us 9 until we get a 0. So we're going to move on to the next number from left to right again. 16 is bigger than 9, so we're comparing it with what we've got as our remainder from our previous subtraction. 16 is bigger than 9, so we're going to put a 0. 8 is smaller than 9, so we're going to put a yes, which means a 1. So we're going to subtract 8 from 9, and what we get is a 1. So we still have a 1 as a remainder. So we still have to keep going until we no longer get this remainder. So 4 is also greater than 1, so we're going to put a 0. 2 is also greater than 1, so we're going to put a 0. But however, 1 is not greater than 1, but it is equal, so which means we can still use it, so we're going to put a 1. So now when you subtract a 1 from a 1, you're going to get a 0 as your remainder, which means this is where you stop. So if you noticed, we finally got in our binary numbers. Let me just erase that, guys, so you don't get confused as a 0 or something else. We have our binary number results here, which is 0, 0, 1, 0, 1, 0, 0, 1. So this is our final result of binary when we converted this denary number into binary. So your final answer essentially is going to be, so I'm just going to replicate writing this here. It's going to be 0, 0, 1, 0, 1. So you read the numbers from left to right, guys. So 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, and 1. So if you count it out, guys, you figure out you get your 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So your 8 bits making up 1 byte. We're going to do the last example here for this video tutorial, and we're going to close it for now. And until I come in our next video tutorial to continue on this unit. If you enjoyed this video tutorial, let me know in the comments. If you have any questions or suggestions, also let me know. I'm open to all of that, and I can cover particular things. But like I said, I'm really going sequential here. So I'm just going to cover the IGCSE sequentially in the curriculum, the IB, and also be doing video tutorials to start from the very basics of programming, which is for Python, up to the advanced, and also for Java. So we're going to be doing the last example of converting denary into binary, and that's 67. So we've done the first one, which was 41. Now we're going to convert 67 into binary. So again, it starts with the same thing again. So you have to have the powers of 2 written out. So we know 2 to the power of 0 is 1, 2 to the power of 1 is 2, to the power of 2 is 4, to the power of 3 is 8, to the power of 4 is 16, to the power of 5 is 32, to the power of 6 is 64, to the power of 7 is 128. So write out your powers of 2 anywhere you have, free space 4, and now look at this number very carefully. Look at what power of 2 can actually add up to this number. So start from left to right again. 128, and then you have to compare them. So 128 is bigger than 67, so that's going to be a no. 64 is actually smaller, so that's going to be a yes. It is possible because it's smaller than 67. So when you subtract 67 from 64, you are left with a remainder of 3. So that's why we said yes, because it was smaller. So we still have to keep going until we don't have a remainder. So 32 obviously is bigger than 3, so we're going to put a 0. 16 is bigger than 3, we're going to put a 0. 8 is bigger than 3, we're going to put a 0. 4 is bigger than 3, we're going to put a 0. However, 2 is not bigger than 3, so we're going to put a 1. That means yes, it is actually smaller than 3. When you subtract 2 from 3, what you get is a 1 left. So you get a remainder. You still have a remainder. We don't want to have a remainder. We want to stop where we get a 0. So basically, we're going to continue. Since we have 1, we're going to look which power of 2 do we have left. We only have 1 left, so whoa, that's surprising. It does match to get our remainder. So we're going to put a 1 here as well, because that's yes, because 1 is equal to 1. So when we subtract 1 from 1, sorry about that, guys, that's like the line. When we subtract 1 from 1, we finally get our remainder, no remainder, sorry, but 0. So that's where we want to stop, because we finally get a 0, so that means that's the end of converting this denary into binary, so that's where you stop. So the final results would be a 0, 1, 0, 0, 0, 1, 1. So I'm going to write it again. So this number in binary is going to be 0, 1, 0, 0, 0, 0, 1, 1. So that's your final answer. So we're going to be stopping this video tutorial for now here, guys. And of course, like I said, practice out what we've learned for today. So what your practice could be is that you definitely should practice from C to J for activity 1.1 on converting binary numbers into denary, and also practice activity 1.2 from C to J of converting denary numbers into binary. So we'll continue in the next video tutorial. I wish you guys a great day, and I'll see you guys next time.